All, one of the important parameter that we see when we select an op-amp is common mode rejection ratio. So for a beginner, it is difficult to understand what is actually a common mode. But for an experienced engineer, definitely he knows the problems of common mode, uh, and definitely knows where does this common mode come from. So we have been very careful in mentioning common mode rather than common mode noise here. So uh, let us see what is the significance of this common mode. So an op-amp basically is a differential amplifier, right? So what is a differential amplifier is basically the output of this op-amp is the difference between the input voltage voltages that is applied on uh, the inverting and the non-inverting terminals. So that means V plus minus, V minus, or whatever we consider as the input voltage. Now that means what actually differential amplifier meant to do is it has to provide gain to a differential voltage. That means it has to provide a differential gain, right? Now in practical scenarios, when we use our circuits on the board, we might have some kind of interference on our circuit due to improper design or from external means. So that noise or disturbance gets introduced onto these rails. Like example, if you see here 2 and 3 example, and that noise could be same in amplitude and phase on these signals. Now considering that we take the difference of the pins 2 and 3 as mentioned here, the non-inverting minus inverting and then multiplied by gain, because the noise that got induced onto this particular pins, as they are same in amplitude and in phase, they must get negated. That means noise must get negated. Similarly, any voltage that is being introduced on these particular pins, like example, if we take the case of a current sense amplifier scenarios where you have a sense resistor, and then at one end of the sense resistor you have example 5 volts, and the other end you might have some 5.02 or whatever. So when you come to the op amp, ultimately it is a difference between them, and the common mode voltage should get rejected, right? That means the common voltage that is there, difference between them should get negated, and only the differential signal should be taken. So this is the simplest way we can explain it, right? So that means common mode rejection is a very important parameter for operational amplifiers. Now if you go back to academics, you might have studied that for an ideal op-amp scenario, common mode is infinite. That means the differential gain should be very high, and common mode gain is very less. That means the gain that is applied to the common mode signals. So the CMRR is generally mentioned in the data sheets by dB. Okay, so the formula for calculating that CMRR is 20 log 10 differential gain by common mode gain. As we say, the differential mode gain should be as high as possible and common mode gain should be as low as possible. That means ultimately we can understand that the CMRR should be infinite, right? That's why in ideal op-amp, but in reality it is not infinite. It could be some value. Now the major problem with the design for the design engineers is what good value is CMRR. Okay, so some data sheets mention that CMRR is 75 dB, some data sheets mention that CMRR is 90 dB, some data sheets mention it as 100 dB. But what is good actually? So as per the practical scenarios that is seen by the engineers worldwide, and considering the advantages of advantage that we get with the common mode rejection, 100 dB could be considered a best scenario. Like example, if you are selecting an operational amplifier, if the CMRR is around 100 dB, that means that op amp is very suitable to give a common mode rejection and apply the gain over the differential signals. So that's a very that's one thing a design engineer can keep in mind. So now, from now on, if you are looking at the data sheet, definitely you can do your own calculations, but if you see a CMRR for an op amp of around 100 dB, that means you can just blindly select it with respect to the CMRR parameter. Now, one important thing with respect to CMRR is CMRR gets varied with respect to temperature, and also with frequency there is a variation of CMRR. Now, while the temperature scenario can be ignored because it won't be too much of variation. Like example, when we say gain drift of the op amp or something, right? Definitely there'll be variation, but we have to live with it. There will be some drift. Now, so considering that scenario, variation of CMRR with the temperature, let us keep it aside, but variation of CMRR with frequency is a very important scenario. So again, this restricts the frequency of operation of the op amp. So as the frequency increases, the CMRR gets reduced basically. So as it gets lowered, that means the common mode gain indirectly is increasing, or the differential gain is getting reduced. That means gain. So we talked about the gain bandwidth product in one of the video previously. So it might be because the differential gain is getting reduced. So that means CMRR is coming down. So this parameter is very important. So while you check for the CMRR value in your data sheet, you also have to look at CMRR variation with respect to frequency to understand if this particular op amp that you selected is suitable for your application or not. So this is a brief on CMRR and what is the best value of a CMRR for a op amp, so that you can choose it comfortably in your application. Please post your comments. Please let us know if you have any suggestions, or if you have any other points, or if you have any concerns about the points raised. Please post them in the comments. Thanks for watching the video.